up, future scientists? This is your Sci Explorer AC, Nikki,
Ahmed, Maki, Christian.
and together we are the Nomenclature Squad.
Good day everyone. My name is Hamed Aldrin Bustamante, and with my group, we will dive into inorganic compounds. Sounds complicated? Do not worry. This dangerous looking chemical is actually just water, aka the hydrogen monoxide. It has a scary name, but it's actually very safe to drink.
Breaking news. Students among grade 11 Latinos in Adzu are panicking over chemical names. But fear not. Your heroes are here to crisscross the confusion away.
Compounds are substances that don't usually have carbon-hydrogen bonds. They include salts, acids, bases, oxides, ionic compounds, and covalent compounds. Today, we'll focus on 5 types: ionic compounds, covalent compounds, acids, bases, and polyatomic ionic compounds.
Inorganic compounds are everywhere. Your toothpaste, soft drinks, or even the tears you cry during exams. But don't you worry, because we're here to make naming and balancing compound less painful than a pop quiz. With that being said, let's Genchem started.
Now let's proceed to chemical naming and formula writing. Let's begin with metal and non-metal binary ionic compounds. Note that the cations always comes first before the anions. Naming cations. Okay, let's go. If the cation is a metal ion with a fixed charge, the cation is named after the element. Examples: magnesium ion, aluminum ion, sodium ion. Occasionally, if the cation is a metal ion with a variable charge or more than one charge, suffixes are used to indicate the charge of the ion. Or, let's go to suffix OUS. Suffix OUS is used for a lower charge ion, and suffix IC or IC is used for a higher charge ion. Example: we have iron with 2 charges. The first one we name it as ferrous because it has a lower charge ion. The second one we name it ferric because it has a higher charged ion. Okay, let's dive deeper. In naming anions, if the anion is a monatomic anion, it is named by adding the suffix IDE to the root of the element or non-metal name. Examples are the following chloride, sulfide, or bromide and phosphide. Let's combine this one. Potassium and bromine, we name it as potassium bromide. Number 2, zinc and oxygen, we name it as zinc oxide. Now let's go to the exciting part. Example number 1, copper with charge 1 and chlorine, we name it as cuprous chloride. Note that we use the suffix OUS since it has the lower charge element. Copper with charge 2, suffix IC since it has higher charge. Another example, we have antimony with charge 3 and sulfur. We name it as antimonous sulfide. We have antimony with charge 5 and sulfur. We name it as antimonic sulfide.
But wait, why did the subscripts of the atoms change?
Nice question, Nikki. That thing is called the crisscross rule. First, write down the cation, the positive ion, and the anion, the negative ion with their charges. Example, antimony with charge 3 and sulfur. Now take the number of charge, ignore the sign, and crisscross them as subscripts. So Sb3 and S2 becomes Sb2, S3. Tada! The subscripts tells us how many atoms in each element are added to balance the charge. Now there you have antimonious sulfide.
Thanks for the help, Ahmed. Now it's your turn to try this.
Okay, Chem Squad! It's time for some polyatomic ions, the portada of atoms that always stick together and never separate. And today, I'll be your tour guide for the world of oxygen ions. So, oxygen ions are polyatomic ions that contain oxygen plus another element. So, the number of oxygen atoms can change, but central atom remains. So, that's why their names follow a pattern. But take note that we also use suffixes when naming them. Have a look. So hypo means least oxygen atoms, I means fewer oxygen atoms, 8 means more oxygen atoms, and per means most oxygen atoms. So let's have an example. Nitrogen oxygen ions. Symbol NO2, we name it as nitrite since it has a lower number of oxygen atoms. The second one is NO3, we name it as nitrate since it has higher number of oxygen atoms. Easy. So let's see if we know this next. So what do you think are the names of these sulfur oxygen ions? Can you guess it? Great. So SO3 negative 2 is sulfite. While the second one, SO4 negative 2, is sulfate. See? Easy. So let's have another example. We take chlorine as an example. So look at these 4 ions. CiO negative is hypochlorite because it's the least of them all. CiO2 negative is chlorite because it's fewer. It has fewer atoms in it. CiO3 negative is chlorate because it has more atoms than the first two. And last but not least, CiO4 negative equals perchlorate because it has most atoms of them all. Okay, that's it.
See? Same chlorine. But it's just oxygen amounts to changing. Now it's your turn to try this.
Okay, Chem Squad, we've already talked about metals bonding with non-metals. What if it's non-metal bonding with another non-metal? That's when we get covalent compounds, the sharing is caring type of bond. Now, the way we name covalent compound is a little different. Take note that the least electronegative element is always written first, then to be followed by the more electronegative element. And instead of using Roman numerals, we use prefixes to tell us how many atoms are present in a compound. 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and lastly 10 is deca. But here's a little secret. When the first element has only one atom, we usually drop off the mono. So we don't say monocarbon dioxide, we just say carbon dioxide. Let's try some more examples. So first we have here CO, or we read it or name it as carbon monoxide, CO2 for carbon dioxide, N2O, or we name it or read it as dinitrogen monoxide. Next, SF6 or sulfur hexafluoride. Next, P2O5 or diphosphorus pentoxide. Pretty easy, right? Since you are Einstein's grandchildren, I have a challenge for you.
Alright, Gem Squad, now let's talk about acids. And no, not that kind that makes your face go overnight, but the ones that release hydrogen ions in water. So, let me share my screen. In chemistry, acids are compounds that contain hydrogen, and when dissolved in water, it produces H+ ions. How do we name them? Easy. It depends on the ending of the anion and also the atomic number. First, if the anion ends in IDE, add the prefix hydro and change the suffix to IC. And lastly, put acid at the end. For example, HCl or hydrochloric acid. Next, if the anion ends in ITE, change the suffix to OUS acid. Example, H2SO3 or sulfurous acid. Next, if the anion ends in ATE, change the suffix to IC acids. For example, HNO3 or nitric acid. Here's a little pro tip for naming acids. Think of 8 or ATE and immediately change that suffix immediately to IC. And when you see a acid that the suffix is ITE, change it into OUS. So it's simply easier to remember and to name the acids. Next, now here's the fun part. the oxyacids. These are acids made up of hydrogen plus a polyatomic ion that contains oxygen. They follow the exact same ITE and ATE rule. So, if the oxyanion ends in ITE, the acid ends in OUS. For example, HClO2, chlorous acid. If the oxyanion ends in ATE, the acid ends in IC acid. For example, HClO3, chloric acid. And don't forget, if you see per-ate, it becomes per-ic acid. As example, HClO4, perchloric acid. So here are more examples below. HCl aqueous for hydrochloric acid. HNO2, nitrous acid. HNO3, nitric acid. H2SO3 or sulfurous acid. And lastly, H2SO4, sulfuric acid. As you observe, the atomic number goes higher each time, so make sure to observe that while naming acids. So, see, it is very, very easy. Now, it's your turn to answer the following.
Okay, Chem Squad, we've talked about acids. Now it's time for the arch enemy, bases. And trust me, they're not basic. Well, actually they are. In chemistry, bases are compounds that produce OH ions, which is hydroxide ions. When dissolved in water, they're bitter in taste, slippery to touch, and they neutralize acids. So if acids are like calamansi juice, bases are like soap. Naming bases is super simple compared to acids. You just name the cation first, then say hydroxide. For examples, NaOH, which is sodium hydroxide, KOH, which is potassium hydroxide, CaOH, which is calcium hydroxide, NH4OH, which is ammonium hydroxide. Bases keep it low maintenance, no drama, straight to the point. But wait, some metals can have multiple charges, and that changes their names. Not all bases are created equal. Sodium hydroxide and KOH, which is potassium hydroxide, that completely disassociate in water. Others are weak bases like NH3, ammonia, which only partly produce OH ions. In this case, we use the rule for naming ionic compounds. For examples, Fe, ferrum, OH2, which is iron, and then hydroxide, which is together ferrous hydroxide, because Fe is 2 plus here. FeOH is ferric hydroxide. Fe is plus 3 here because there's Fe, OH, and then 3. That's why it's called ferric hydroxide. CuOH, cuprous hydroxide. CuOH2 is cupric hydroxide. Got it? Now I have a challenge for you.
Let's have a short review before we proceed. Chemis represents chemical reaction through symbolic representations called chemical equations. The chemical formulas found on the left of the arrow are the starting substances called reactants, while the chemical formulas found on the right of the arrow are the produced substances called products. The numbers beside these chemical formulas are called coefficients, which indicate the relative number of molecules of each kind that involved in the reaction. Take a quick look at these symbols that are used in the chemical equations. In writing chemical equations, always remember that the rules in writing chemical formulas of the compound must be followed. Hence, the crisscross rule is applied in writing chemical equation. Rule number 2, if an element is gaseous at room temperature, then it must be represented by its natural molecular formula. So for diatomic gases such as hydrogen, fluorine, chlorine, oxygen, bromine, and nitrogen, it is written as H2, F2, Cl2, O2, Br2, I2, and N2. Or just remember the acronym, have no fear of ice cold beer. And for monoatomic gases such as helium, neon, argon, krypton, and xenon, it is written as He, Ne, Ar, Kr, and Xe. Rule number 3, a solid element can be denoted by the subscript small letter s, a liquid element by the subscript small letter L, and a gaseous element with the subscript small letter G. So now you are ready to balance equations. To illustrate the process of balancing a chemical equation, consider the chemical reaction. Hydrogen reacts with oxygen, produces dihydrogen monoxide. So the first step, we have to write the skeleton equation for the chemical reaction, or the given. Determine the correct formulas for all the reactants and products. The reactants must be written on the left and products on the right, which are separated by an arrow to indicate yield. If 2 or more reactants or products are involved, the formulas are separated with a plus sign. Also, the physical states of all reactants and products must be shown. So step number 2, count the atoms of each element in the reactants and products. So in this example, for the reactants, we have 2 atoms of hydrogen and 2 atoms of oxygen. And for our products, we have 2 atoms of hydrogen and 1 atom of oxygen. So as you can see, our equation is unbalanced since we have 2 atoms of oxygens rather in the reactants, while in the product, we just have 1 atom of oxygen. So how do we balance it? So here comes step number 3. Balance the element one at a time by changing the coefficients. Take note that it is understood that the coefficient is 1 when no coefficient is written. So we begin by balancing elements that appear only once on each side of the chemical equation. So let's try to add coefficient 2 on the hydrogen. So here we add 2. So let's just multiply it by the subscript. So we will have, for the reactants, 4 atoms of hydrogen. So to balance it, let's try to add 2 in the product. So as you observe, when we multiply the coefficient 2 to the subscript 2 of the hydrogen in the products, we will also have 4 atoms of hydrogen. And of course, since the products is the substance produced by the reactants, so of course we will also multiply the 2 or the coefficient 2 rather in the oxygen. So now we have 2 atoms of oxygen. So as you observe, this equation is already balanced because for the reactants we have 4 atoms of hydrogen and 2 atoms of oxygen, whereas the product has also 4 atoms of hydrogen and 2 atoms of oxygen. So there you have it, it's already balanced. So take note that trial and error is applied in changing coefficients when balancing a chemical equation. Also, fractions and decimals are not allowed in the final formula. So for step number 4, check whether the number of atoms or polyatomic ions are equal on the both sides of the chemical equation. So there you have it. As we already checked it earlier, it's already the same or it is already balanced. So okay, let's just rewrite the balanced chemical equation. So we have 2 hydrogen reacts with oxygen, produces 2 molecules of water or 2 dihydrogen monoxide. So there you have it. It's kind of tricky, but at the same time easy, right? So now for your final challenge, try to solve the following. And that wraps up our chemistry adventure for today.
Chemistry might look scary at first, but once you break it down, it's just atoms finding their perfect balance.
Because if hydrogen and oxygen can work together to make water, then maybe my crush will finally work with me too.
Seriously though, chemistry is everywhere in our daily lives.
So keep exploring, keep learning, and don't be afraid to experiment.
Thanks
for watching.
This has been the Nomenclature Squad. See you next time!